Hi, everyone. My name is Yaron. I'm CTO and co-founder of Iguazio, a data science platform company. What I'm going to talk about in this presentation and demonstrate is how to accelerate production of machine learning and data science workloads using microservices architecture. First, before we dive into the solution, let's understand the problem. The key problem today for many organizations is how to move from research environments where they do experiments of machine learning workloads, usually working off a small data set using CSVs, Excel spreadsheets, running some analysis and data science on their Jupyter notebooks, and finally doing some iterative work and throwing that into production. The problem is that when you're going to real production, the workloads look pretty different. You have real data which runs at scale. Data may be streaming, may arrive from operational databases through ETL. You may need integration with real APIs that produce additional data. Once you've brought all the data into the system, you have to run preparation at scale, not on CSVs and Excel spreadsheet, but on rather large files or actually work against databases in order to denormalize and create meaningful features off the data. And that requires larger scale and more distributed systems. But once you've done that, you want to run machine learning, and even at that phase, you want to apply automation. You want to use every time you change a model, you change the data. You see a drift happening to your model. You want to retrain, and maybe even with multiple versions of parameters and algorithms in order to guarantee that you have the maximum accuracy. So that needs to go through automated mechanisms and again work on large data sets. And finally, when you have the model, you have to serve that model in production against real-time data, real features that come from streams, from transactions, from user requests. And you want to be able to monitor your models in real time, elastically scale them as needed, and create sort of a feedback loop back into the training and data preparation. When you're starting to do that, you understand that the basic principles of developing in research, essentially doing jumbo Jupyter notebooks with a lot of code, are not really applicable to production. This is where usually large teams of people come into the picture, DevOps, MLOps, data engineers, ML engineers, whatever, in order to deliver everything. And in many cases, they happen to rewrite the code from scratch. So what we want to try and do is be able to build architecture that encompass the production requirements already in day one. So now just to understand further, what are those things that you need to apply to a workload before you make it production worthy? So in this diagram, you can see that once you finish developing the code, it's not enough to have code. The next thing you need to do is essentially package it, create Docker containers and make and build scripts and test scripts. And then you need to think about scaling out your code. And there are different scaling strategies depending on your workload, if it's data analytics or machine learning or deep learning. And once you've done that, you have to apply optimizations to make sure that it performs pretty well, because this model serving function may sit behind an API gateway and serve real customer requests. If it takes too long, the latency is too high, it may not respond in time, or maybe it does not have the right throughput to support your business application. And in order to provide a production-aware system, then you have to apply monitoring, observability, logging, security, versioning for everything, so you can further explain and understand what's going on in production. And what you want to apply in order not to do everything manual, you want to apply automated processes. So CI/CD, continuous integration, continuous development, creating workflows that automate the work of productizing or generating those models and the data sets that are relevant, doing rolling upgrades so you don't have downtime, potentially doing A/B testing and canaries. So there are many operational aspects to building a machine learning pipeline and workflow. And what you end up doing with a couple of data scientists for a few weeks, you may have, what we hear is people spend 12 to 18 months trying to productize those artifacts, because they need larger teams with different disciplines that work on that problem. And what we're trying to show here is how to automate most of that workflow so we can rapidly go into production. So if we're Zooming into what is a machine learning pipeline, so we have three different layers. We have the data layer, we have the computation layer, and the pink one is sort of the automation and orchestration layer. So usually in a pipeline, you have different forms of data. You're starting with raw features that are being ingested through external sources using ETLs or stream or various other mechanisms. Once you have the base features, you need to run analysis on those data sets. And the analysis will produce a new denormalized data set or clean or aggregated data set that we want to use for the training. So here in the preparation, we may use tools like Spark for analysis or other Python tools or various database capabilities. Once we do that, we apply training. And in the training, we want to try and do through parallelism, we want to try different forms of training, different algorithms, different parameter combinations in order to see which one results with the best accuracy or best performance. Sometimes it has the best accuracy, but it lowers our performance significantly, or it takes a lot of time to compute it. It's not really worth the extra accuracy. On the other time, once you've done the training, you want to run validation, and the validation will take a bigger data set and contrast that with the model that we just created, validate it, it's working, performing, etc. And once we have that ready, we move into deployment. So this, when you do deployment, you actually deploy two different things. You deploy the model, but you may also need to deploy APIs that go and query the data, bring the feature vector, and essentially launch a call against the model. Those two things, the deployment of the model and the APIs, they also generate a lot of telemetry and a lot of information that will later be used to help us monitor the models in production, try and detect drift, detect all sorts of anomalies, monitor performance behavior of our model, etc., which also feeds back into the beginning, because if we find some changes in the model, then we may want to do retraining and collect new data, etc. Above that layer of computation, we need an orchestration. We need to monitor the experiments, monitor the data changes. We want to orchestrate. Don't want to run everything manually. We want some automation system to build those pipelines for us and monitor their activities, as I mentioned before. So in our solution, we have those three layers. One comprised of sort of set of managed data services, and the other one comprised of a set of serverless function engine that we'll describe based on few tools that can run different engines, whether it's Spark or functions more oriented towards real time. And above that, a set of orchestration tools based on several open source projects. Okay. And so if we need to build a stack, one of the recommended mechanisms is to essentially leverage Kubernetes, which is a generic microservices orchestration framework. And on top of that Kubernetes layer, we want to plug all those different services, including Spark and potentially Presto and TensorFlow, Horvo, Jupyter Notebooks, serverless engines like Nucleo, etc. This layer has to use some data because after all, we're processing some data. So we may have a combination of, on one end, a data lake. In the cloud, we may use S3 or Object Store. On-prem, we may use some file solution like NFS or Hadoop, HDFS. And in parallel, we may want databases to do more real-time workloads and querying, key value stores, etc. At the end, on top, we need a framework to also run the AutoML, run various experiments automatically. We need a way to track the experiments, the data that is resulting from the experiments, etc. We need a mechanism to manage the metadata of all of our data sets and the features through a feature store. And we need a workflow engine. There's one pretty good in Kubernetes called Kubeflow, which is very tightly integrated into Kubernetes. So that is essentially a recommended architecture for building your microservices. So we talked before about the concept of serverless. So serverless was invented 2 years ago by Amazon with the introduction of Lambda. Serverless is trying to enable two main things. One is provide resource elasticity, which translates to lower cost because you're only using what you need. And on the same time also translates to scaling out and being able to handle any scale of data and computation needs. The other aspect of serverless is it essentially automating all those different tasks that I mentioned before. You don't build containers. You write a function, and that automatically runs on some container that's generated for you. Everything is auto-scaling. It's monitoring the workload automatically and logging, and it has more rigid security. And all the things are automated, so we don't have to deal with those aspects. But serverless also have downsides, and I've listed them here in the slide. So you can see serverless is usually event-driven, very short lifespan of functions. But when we drive a machine learning workload, it may work for half an hour. And also scaling it done through serverless using load balancer techniques. While, for example, you take Spark, then the Spark scaling is done for RDDs and shuffles and reduce. Or in machine learning and deep learning, using hyperparameters to run multiple permutations. So that's a different way of scaling the workload. In data science, you have state, you have data, and usually serverless is stateless. And finally, the inputs and outputs of a function in those kind of data intensive job is more like a job, meaning a parameter, a data set. You input a set of parameters, you provide some input data set, and you output with a set of results and some output data sets. So we need a different API to those serverless functions, but the general idea could stay the same of having essentially elastic scaling and doing fully automated deployment and operation. So with that, we introduce an open source framework tool, actually, one called Nucleo. Next, sorry. One called Nucleo, the other one called MLRun, which work together. And the general idea is to abstract the computation resources. And computation resource could be a Spark cluster, could be a DAS cluster if you need, could be Horvath if you're using deep learning, or Nucleo engine, which is used mostly for real-time surveying, ingestion, etc. And you take your code, you plug it into that runtime, but you need an automation framework to do all those things that servers do: build containers automatically, auto-scale the workloads, collect inputs and outputs, do logging, monitoring, etc. So we came up with this concept of machine learning functions, which is essentially doing all that work for you. Think of it as when you have a function, what you want to do is inject a set of inputs, parameters, secrets, credentials, in case you're accessing some databases or external connections, and some data sets. Then you want to run your workload and finally generate outputs from that function, which could be results, accuracy, etc. It could be operational data, logs, monitoring, etc., or it could be data itself. And those functions need to plug into a framework for workflow management and workflow orchestration, so you can compose different workflows out of those individual function objects. Okay, and one of the tools that we use for composition is an open source tool called Kubeflow, originally designed by Google, which allows you to compose, if you're familiar with Apache Arrow or Jenkins in the DevOps world, so you can essentially go and compose a layout, a graph, a DAG, and say, for example, go bring the data, you finish bringing the data, run some data preparation, run training, validation, deploy with a bunch of conditions. So you can use Kubeflow, and if you combine Kubeflow as a workflow engine with serverless frameworks like MLRun and Nucleo, then you can essentially go and create something which is far more automated and deliver those pipelines without all the DevOps work associated with that. Okay. So if we're looking into a workflow, how would such a development workflow work? So usually you start with writing some code. So you write code in your local Jupyter or PyCharm or in a managed Jupyter notebook or some other notebook framework. While you're doing that, you may still want to track everything you do, runs, experiments, and you need some SDK for that, like MLflow or MLRun has its own mechanism for tracking experiments. Once I want to move to run the job in the cluster, I may need to also specify some resources. For example, I need GPUs. I want a certain amount of CPU. I need dependencies on certain images. Maybe I need to mount some data volumes into my workloads to make my workload work against that data. I need to specify that. And then there's an automated machine, part of any serverless engine, that will do the build for me and the deployment on the cluster. So I can deploy in the cluster. I can run now at scale. For example, I could write a Spark job or any other Python job on my notebook, add some configuration and metadata for the runtime on that job. For example, I need this image, I need this amount of CPUs or GPUs, and launch. This launch will trigger a build process and a deployment process. And my job can now run distributed on the cluster. And we're going to see that in a minute, how I can run, whether it's a Spark job or regular Python job on the cluster distributed, with just simply submitting the work. Once I finish experimenting with my function, unit testing that, I want to publish that into a source code repository like GitHub, for example, potentially adding some documentation. So if I later on want to go back into that function and use it, I know what it's doing, what's the API, etc. Or I may want to compose a bigger workflow using Kubeflow pipelines, which essentially does a multi-stage process. For example, prepare data, train, validate, etc. When I'm building the pipeline, I may also take functions that were built before, either by me or by other members of the team. So this functional programming is allowing me to break my code to smaller pieces that are managed, could be versioned, could be deployed in a more easy way and are fully documented. And I could use experiment tracking for the entire system to see what's going on. So that's one type of workflow. Another automated workflow that is more what is referred to as GitOps, Git-based operations, or the traditional CI/CD workflow, is that instead of publishing your code at the end, you write some code and you provide some manifest, some configuration, and you publish that into a source control system like Git, for example. This pull request generated triggers, which automatically takes your code, take the dependencies, build the images, runs automatically the pipeline, reports on the results, and responds back into your pull request, responds back with all the results of the training or the workflow, and you can take it for that. That's the benefit of that. It's more production oriented because you can track the entire process. You could see who published. You can have reviewers that approve the process, etc. But those two processes will coexist. Usually in the initial development of a project, we'll start with a more interactive way. And as we introduce more members to the team and we grow, we have to move into more and more automated CI/CD-based pipelines for our workload. And we'll see how we can essentially combine both in an automated fashion. So with all that theory, let's look at the actual deployment example from one of our users called Payoneer. They're doing a fraud prevention. They're a payment company, pretty large. They wanted to do two things. They want to move from fraud detection to prevention, meaning becoming more real-time, and this provides a lot of value to their business. On the second aspect, they want to move to a microservices architecture, which cuts the time for them to productize any new software artifact, any new thing, bring it much faster to production. So they've chosen to move from a traditional architecture, which is Hadoop-based, to an architecture of microservice. So their original solution, by the way, there's a full case study. Anyone that will send me an email, I can send him the case study on that. The original solution based on Hadoop was essentially doing ETL jobs from their database, running various analytics workload, and then using using R server to do predictions. The process, because it was very batch oriented, took about 40 minutes from the minute the transaction were written to the database until they could decide if they want to block the fraudulent account or the fraudulent transactions. And that's really challenges because in 40 minutes you can empty the bank. The other challenge that working with Hadoop, it was very rigid. The process was very resource intensive, and they wanted to move to a more agile, automated microservices architecture, pretty much like in the cloud. So with that, they changed into a new architecture based on real-time and microservices. So the general idea is that the database transactions are streamed. They're not batched. They're streamed into serverless functions that collect this stream. Once the serverless function gets intercepts a stream, they run first analysis or enrichment or other aggregations on the data and ingest that into a real-time feature store. In parallel, we have Spark functions that run analytics functions on a bigger window and trying to work and create additional insights from the data. We have now an enriched data set from historical data and real-time data. So we have functions that essentially go and do model training. In this case, they use scikit-learn in a distributed fashion. And once we have those models, we can start serving those streaming events. So all those streaming events that are come and getting contextualized and enriched in real time into enriched feature vector are going into an inferencing serverless function. This serverless function decides if to block the account or not, and it essentially just writes into the database telling the database block this account because there is a fraud. And so this entire process from getting the data out of the database on the first transaction that is suspicious in fraud until the account was actually blocked, this entire process took about 12 seconds, moving from 40 minutes. Why? Because it's much easier to do those kind of things with serverless functions and streaming or message queues in this example. And you can see that we combine traditional tools like Spark alongside with other sort of more Python or other languages in a microservices and containerized workload. The major advantage beyond cutting the time to detection is also moving to an automated development and production environment using this serverless approach. If we want to change a piece of code in any of those tiers, we just go and update something and push deploy, and it gets deployed into production. There's no need for long build processes, etc. It's very automated workflow. And in a rolling upgrade, it will actually, without incurring any downtime, it will automatically update in production. So this customer managed to move from a quarterly release cycle to a weekly release cycle because it's so easy and automated to release new versions into production. And it's rather safe because they can always pull back and load the previous version. Now, once we created a model, it's not enough. We need to monitor our model in order to identify if the model is bad, if it's good, if there is a drift, if there's a problem with performance. Maybe we need to switch back to an older model or retrain or create ensembles. So we also need a real-time system to monitor our model in production. So using this serverless or microservice architecture, once we've done the training and we created the serving API and model, those serving API and model also generate a stream of data with all the transactions of inferencing that entered that system. There is a microservice that listens on that stream and starts analyzing that stream, creating time series aggregations, which we'll show later on in a dashboard like Grafana, and essentially micro-batching those streams into bigger Parquet files. And there is another function that periodically goes and analyzes that stream of data and compares it with reference data in order to detect that there is drift. If there is a drift, through a simple API calls, it could launch a modify an ensemble or do any corrective measurement. So it's now not only the problem of creating the training and serving the model, we also need to be able to manage the model and monitor the model in production. Okay, so with that, let's go and see a demo of this architecture in action. So what we see is what we want to show you is how it's relatively easy to go and start with a notebook and write some code and turn that code into production without a lot of work. So we see here a notebook running on our managed platform, but that could also be running on your laptop. There's full documentation on that. That is using a project called MLRun in GitHub. MLRun has a repository in Git that you can just go, and there's a lot of demos, end-to-end demos of different use cases, image classification, face recognition, time series analysis. You can just load the project and go with it and start, customer return prediction. This is an entire project with many different complex steps that could be, tried out through that project. So let's take this simple example of a project that's just using the iris data set. So what we said before, that we need to provide a manifest along with our code. So our code is the code that is running, but sometimes we need some packages or we need some images or resources. So we can just annotate those in our notebook and give some commands to serve a compiler that will come later, that those are packages that are required for production, or this is the image we're going to use as a baseline Docker image, or potentially, again, multiple other configuration. Then we could just go and run or write our code, and we could instrument our code. We could also add things like logging artifacts or data sets or models, or just logging and notifications and grabbing some secrets and credentials, or all sorts of things that are provided through the wrapper that runs this code. And again, it's very simple code. There's a context object. There are certain parameters that are injected into my code, and I could just go and run it as a data scientist and play with it. At a certain point, I want to create a project that uses a bunch of functions, so I can just go and create a new project. And I'm going to run my code in my notebook by just wrapping it with something that will sandbox my code and record everything that my code did. So I'm using run local, and I can run it. At the same time, exactly, I can just go and run it on the cluster as if it was running on my notebook. So that also allows me a concept of CPU or GPU as a service. So I can just launch a job on the cluster. At some point, I want to turn my code in my notebook into a container object. So that's relatively easy. I just run a command called code to function. I give it a name, a runtime engine. Again, could be job, Kubernetes job, or could be a Spark job, or other things supported through that engine. I may want to register my function to my project, so that will appear later on as part of my project. And maybe I want to start doing other things. Like, for example, I want to analyze my data. I'm going to use a library function called describe with a certain tag. And because that function is already showing me how to go and analyze the features and the clustering and all that of my project. So I'm just going to load this function. I don't really remember how to use it, so I just ask for documentation. And you see, I understand what this function is doing is visualization and data analysis on the data set. I can provide it all sorts of parameters. And then I just want to run this function. I loaded it from the internet with a certain version. I want to run it with certain parameters. What is the label columns? What is the input data, which is essentially the output of my previous job that I was running. Just pointing to it. Where do I want to drop my artifacts? And I'm just going to launch this job. Now, if you're familiar with Kubernetes, you'll see that actually in the background, it's creating a job in the cluster. But all those outputs that are generated from the function are going back to my Jupyter. So I have the experience of running from a notebook, but in parallel, it's actually running on a distributed cluster and recording all those actions. At a certain point, I want to create a bigger pipeline that involves scikit-learn classification with AutoML and potentially testing my classifier using distributed validation techniques, and creating a model serving function. And after I created the model serving function, I want to test that it's actually working and performing to order. I don't want to write all this code. I'm too lazy. So I'll just import functions that do all those things for me. And I'll add them to my project. And the only thing I need to do now is define a DSL, a graph that tells me, run the ingestion, finish the ingestion, good, run the analysis. Once you finish the analysis, run the training. And once you finish the training with, various algorithm options, because it's AutoML, it will automatically run through all of those, run the validation. The validation will use the data and the test set and the model from the training, and so on. The serving function, we use the model from the training, and the live testing function will use the addresses and other things from the deployment function. So I essentially define a graph, and I could just go and execute that graph by just saying project run, okay? And what it does, it essentially creates a kubeflow, a Kubernetes automated workflow with all of those things that I just described. So you see, I have a deployment, I'm building my containers for the setup, and then I'm getting some data. Data is presented here. I'm summarizing my data, I'm running analytics and feature analysis on my data, so I can see the behavior of my data, the features, again, all sorts of charts automatically generated for me. I want to run training. So again, I can see our C curves and various charts that are generated through the training. The training is also doing AutoML, and so I can actually see that it's ran multiple algorithms on the same data set. Once it's done, I see testing on the model with, again, different test set. It's deploying my model, and after deploy the model, it's actually testing that my deployed model is performing. This is like a latency curve of my model. So I fully automated my entire pipeline by writing a single notebook. I created an end-to-end project, something that would take months and months. And it all scales on a horizontal scaling cluster. Now, it's not limited to just those simple Python functions. You could do exactly the same with also Spark. So MLRun supports Spark as a runtime engine, and I could define Spark job, a task. This is a task that, for example, reads a couple of data sets and runs some query and some joins on those two data sets. So I define parameters to my function, which are the source data sets. I define a SQL query, which I want to run. And I have some Spark code that is in the background. I can run this thing using a local, what we call local runtime. So I'll run it locally on my notebook environment. Great, it works. And then I can run it on a distributed, as a serverless Spark function on a distributed cluster by just changing my runtime kind to Spark. Now it's essentially using Kubernetes operators. If you're familiar with that term, essentially it's going to launch a Spark cluster for me and run the job on that Spark cluster. And I could customize resource requirements and dependencies and jars and all of that. So again, with this mechanism, you see that I can fully automate my productization pipeline. I can get really nice performance. All those functions that I'm building are part of Nucleo, again, an open source project where I could just go and view those functions, dig into the code of the functions, and I can attach those functions not only as batch, I can make them work off streams, like, for example, Kafka stream, etc. And just spend a few configuration elements on that. And the other thing I mentioned before is beyond just doing all those things manually, we can also work for everything in a Git-based workflow. So we can, for example, publish our code, this notebook that I just mentioned. We can just publish it into Git, to GitHub in this example. The code is also generating what we call a project YAML file. It's the project configuration file of all those things that I did, those functions that I attached, some other configuration. And what I can do is every time I change the code through a pull request, let's take a pull request example, I can ask the Git to just run experiments on that workflow of my repository. This trigger will automatically launch a CI step. So automatically, MLRun will kick in. It will automatically respond. That's a comment made by the bot. It's automatically responding. I'm starting to run this pipeline that we just showed you. When the pipeline finishes, it will automatically plot a result. So this way, we manage to document the entire workflow. We can have reviewers. We can have a much more controlled workflow for our development. So without a lot of extra work, we just converted something that we've worked on interactively into a fully automated CI/CD pipeline for machine learning. Okay, so with that, thank you, everyone. I hope this demo was clear. Anyone that wants to ask more questions, you can reach me out. In my Twitter is my full name, Yaron Haviv. You can find me on LinkedIn, and I'll be happy to assist any of you if you have any questions.